Look at this interesting question. We are given here the case of a soap bubble which has a small negative charge. We have four options given to us about the radius of the soap bubble. Look at the options. Decreases, increases, remains constant, first increases and then decreases. Well, how do you answer this? You have to visualize what's happening here in order to answer this. First of all, it is safe to assume that this soap bubble is given a uniform negative charge distribution. So, let's consider a soap bubble with a uniform negative charge distribution. Consider a tiny portion of the outer surface of the soap bubble. Look at this. Here are the negative charges, and obviously they are going to exert on each other a repulsive electrostatic force. As a consequence, they try to move farther from each other. And as a consequence, the soap film will stretch. And what happens then? The soap film will stretch and the soap bubble will increase in size, and therefore the radius of the soap bubble will also increase. That's what happens. Now, with this information, let's look at the options given once again. Which one do you think is the correct one? It's obviously option B. The radius of the soap bubble increases. Let's move on to the next question. It says, it has been observed that after rubbing the comb with hair, it starts to attract tiny pieces of paper. Identify the correct statement which explains the above phenomenon. Look at the options. Combing the hair leads to charging it by induction. The comb became charged by friction and it caused redistribution of charges in pieces of paper when brought close to them. Next one. Comb gets charged and attracts the tiny pieces of paper by conduction. And the last one. It attracted tiny pieces of paper due to cohesive forces. Well, in order to answer this, first of all, you have to understand why does the comb even get charged in the first place? Why does the comb get charged? When you move the comb through hair, the electrons from hair will get deposited on the comb. So, the comb will become negatively charged, leaving behind effectively a positive charge on the hair. What is happening here? In other words, redistribution of charge. Remember, in any charging process, the charge is neither created nor destroyed. It is simply redistributed. So now you know why does the comb get charged. Let's understand what happens when the comb is brought near some pieces of paper. Well, we are assuming that these pieces of paper are neutral to begin with. In that case, the nearer side of the paper, which is facing the comb, will get opposite type of charge induced on it. We know that comb is negatively charged now. So, the opposite type of charge, which is positive charge, is induced on the nearer side of the paper. On the farther side, it will be negative charge. The effect is such that the pieces of paper will get attracted to the comb. That's what is happening here. Now, with this information, let's look at the options once again. You will see that the correct one is option B. The comb became charged by friction and it caused redistribution of charges in pieces of paper when brought close to them. Next, we have a beautiful question on the application of Coulomb's law. We have here four positive charges given to us, each of magnitude 2 root 2 minus 1 into capital Q, and they are arranged at the four corners of a square in a horizontal plane. There's another charge, small q, which is placed at the center of the square, and we are supposed to find the value of small q such that the resulting force acting on each corner charge is 0. How do we do that? Well, this is a regular square in the horizontal plane. If we are considering the net force acting on either of these corner charges to be 0 in this horizontal plane, then we need to consider the forces acting on either of these charges in the plane itself. Which are the forces acting on any of these charges along the plane? It's supposed to be only attractive or repulsive Coulomb forces. Now we know that these four charges are identical in nature and magnitude. So it can only be Coulomb's repulsive force. In that case, if, for example, if we consider Q1 here to be in equilibrium, then the net force acting on that charge has to be 0. In which direction? In any direction in the plane. Because of this charge, there is a repulsive force in this direction. Let's call it F1. Because of this charge, there is a repulsive force in this direction. Even this will be F1 in magnitude. Why? Look at the Coulomb's law. F, the electrostatic force of repulsion or attraction between two charges Q1 and Q2, will be proportional to the product of these two charges and inversely proportional to the square of the distance of separation between them, R square. And here is a proportionality constant, capital K, coming in. Now, in both these cases, Q1 and Q2 are same in magnitude and even R is same. So, this force and this force are same in magnitude. Now, what about the force of repulsion between this charge and this one? Obviously, it's in this direction. It will be different in magnitude because the distance of separation between these two charges will be different this time. Do you notice that the resultant force, because of these three forces, happen to be in this direction? Because this is 45 degree, this is 45 degree. If you resolve the components of F1 each time, you see that they add up along this direction. But we know that this charge Q1 has to be at equilibrium. And the only way it can happen is when there is a balancing force in the opposite direction. That is, in this direction. And that can happen only when the small q that we choose to place at the center of the square happens to be negative in nature. In that case, there is an attractive Coulomb force in this direction which balances out the force in this direction. Applying Newton's second law, for this force balance condition, we can obtain the magnitude of small q in terms of capital Q. Let's do that. Here is the diagram once again. You know that this is 45 degree and this is 45 degree as well. So, the resultant will be in this direction. How much is it? 2 times F1 cos 45 degree. And there is already F2 in this direction anyway. Now, what is F3? It's a force of attraction between small q and capital Q1. These forces add up to become 0 along this line, isn't it? So, if you can state that mathematically, it can be written as F3 must be equal to 2 times F1 cos 45 degree plus F2. Now, how do you find F1 or F2 or F3 for that matter? It is from the Coulomb's law. F1 happens to be K Q1 square by A square. What about F2? F2 happens to be K Q1 square divided by root 2A whole square. Why? Because the distance of separation between this charge and this charge happens to be root 2 times A. What about F3? Let me write it here. It will be K small q capital Q1 divided by this distance squared, which is A by root 2 whole square. Now, let's put all that in this equation. What will you get? You get K small q capital Q1 divided by A by root 2 whole square equals 2 times K Q1 whole square by A square into 1 by root 2 plus F2, which is K Q1 square by root 2 A whole square. Let's simplify this. What do you get? You get Q divided by 1 by 2 equals, this will be root 2 times capital Q1 plus, what was this? Q1 divided by 2. Let's simplify this. You get Q is equal to 1 by 2 into 2 root 2 plus 1 divided by 2 into Q1. But we already know the Q1 value. How much is it? 2 root 2 minus 1 into Q. Let's substitute that. You get small q to be 1 by 4 into, look at this. You have 2 root 2 plus 1 into 2 root 2 minus 1 into capital Q, which will give you 2 root 2 whole square minus 1 square into capital Q. And that will be Q is equal to, what is 2 root 2 whole square? 8. 8 minus 1 is 7. So 7Q by 4. Is the answer 7 capital Q by 4? No. That's because we determined that this charge, small q, has to be negative in nature in order to produce an electrostatic force of attraction between small q and capital Q1. So, the correct answer is minus 7 capital Q by 4. This is only the magnitude because we consider the direction of forces already. This is your final answer. Now, let's look at the options once again. Obviously, the correct option is A. Look at this question here. We are given 3 particles, each of mass m and carrying an identical charge q each, and are suspended from a common point by insulating massless strings each of length L. If the particles are in equilibrium, what do you mean by that? The net force acting on either of these particles is 0 and are located at the corners of an equilateral triangle of side A, then calculate the charge small q on each particle. Well, here is the diagram and these are the options given. We are supposed to find the charge on each of these particles so that each one of them is in equilibrium. That should tell you that you have to apply Newton's second law to establish an equation to obtain small q value. Well, these charges are in the horizontal plane. So you need to consider the net force acting on either of these charges along the horizontal plane. If you consider one of these charges, let's say this one, take all the forces acting on it, resolve those forces along the plane, add them up, and they should give you 0 in magnitude. That's what it means. Alright, let's do that. Here is a charge q in consideration at position A. First, let's consider the Coulomb's electrostatic force of repulsion acting on small q. One force is because of this charge, another force is because of this charge. Do you notice that because of the symmetry of the situation, these charges are at the corners of the equilateral triangle. Now, this happens to be 60 degree and so is this angle. In that case, the net force, what do you mean by that? There's one force here, another force here, F each in magnitude, and the net force of repulsion happens to be along the bisector. Let's call it F prime, making an angle 30 degree each with these two forces F each. In that case, F prime happens to be 2 times F cos 30 degree. Also, since we are looking at the equilibrium condition or the force balance condition for the small charge Q, let us consider all the other forces as well. Here is the tension acting along the string. Let's call it capital T. And if you consider this angle to be theta that the string makes with respect to vertical, then obviously even this angle is theta. This is T cos theta and this is T sin theta. There's force of gravity acting on the mass mg in the downward direction. So, if you consider the equilibrium or the force balance and take x-axis and y-axis as shown, apply Newton's second law and obtain an equation for force balance along x-axis and y-axis separately. What do you get? You get F net, which is F prime itself, balancing T sin theta, and you also get mg to be equal to T cos theta. But then again, how do you find this F prime, which is 2F cos 30 degree? What is this F here? It's a Coulomb's electrostatic force of repulsion between any two charges given. And that is given by Coulomb's law. It states that if you take two charges, Q1 and Q2, separated by a distance r, then the force of either attraction or repulsion between them, depending on the nature of the charges of course, is 1 by 4 pi epsilon naught Q1 Q2 divided by r square. And in this case, the distance of separation happens to be a and the charges happen to be q each. So F is 1 by 4 pi epsilon naught into q square by a square. So let's take that into account. This will be giving us tan theta equals, how much is this by the way? This is root 3 times F, isn't it? So you get tan theta to be root 3 F by mg. What do we need? We need the value of small q, which is contained in capital F. We need that in terms of m, g, a and so on, not in terms of theta. So let's find an expression for tan theta in terms of the length of the string and small a first. How do we do that? Well, let's consider this diagram. Here is the string of length L. If you look at the vertical height here, which meets the centroid of the equilateral triangle, this is height h. But we also know that L is much greater than small a. What does it mean? It means that h is almost equal to capital L itself, because small a is really smaller in magnitude compared to capital L. Now, we know that this is theta and this distance, the corner to the centroid distance in an equilateral triangle, happens to be side length divided by root 3. And what is the side length here? A. So this happens to be A by root 3. Now, look at this right angle triangle. PAO. Do you see that tan theta from here can be written as A by root 3 divided by L, which gives us A divided by root 3L. And we already know what is tan theta in terms of F. It is root 3 F divided by mg. And what is F? Here it is. Let's substitute and find out the value of small q. What will it give us? It will be A equals 3q square by 4 pi epsilon naught A square mg, and there is L here. Alright. Let's take an expression for q square. You will get 4 pi epsilon naught A cube mg divided by 3L. What do we need? We need small q. So we need to take the square root on both sides, and that will fetch us the value of small q. How much is it? 4 pi epsilon naught A cube mg divided by 3L, and the whole thing under square root. That's your final answer. That's the value of small q such that all these three particles are in equilibrium and at the corners of an equilateral triangle as shown. The correct option for this question happens to be B. Look at this beautiful question on application of Coulomb's law. Here we have 2 point charges Q1 and Q2 separated by a distance small d, and they are in vacuum. The force acting between them is called capital F. Now, this situation is changed a bit. There is an insertion of a dielectric slab of thickness small d by 2 and of material with dielectric constant k is equal to 4 between them. We have to find the new force between the charges now in terms of capital F. How do you solve for this new force? Let's call that F prime. How do you do that? Well, what comes to our help is the Coulomb's law. The charges considered here are the same. So from Coulomb's law, we know that the dependence is only on the distance of separation. The Coulomb's force between two charges at a certain separation distance d happens to vary as the inverse of the square of the separation distance. In the first case, it is small d. Even in the second case, it is small d, but there is a dielectric slab between them. So, can you compare these two forces as they are? No. The best way to compare these two forces is to subject them to the same circumstances. What do you mean by that? Let's take equivalent air length or equivalent separation distance in air between the two charges for the given changed situation, and then compare the forces obtained in these two cases. Alright? In first case, the charges are separated by a distance small d in air itself. So that force F is proportional to 1 by d square. Let's call that equation number 1. Look at the second case. Now, the force is called F prime. To calculate the equivalent distance in air, let's look at the setup here. D by 2 of the separation distance is in air itself. So, the equivalent air distance is d by 2 itself. So, in second case, F prime will be proportional to 1 divided by d by 2 plus the equivalent air distance of separation for this setup square. And how much is that? Simple. A distance or a length of d by 2 in a certain medium is equivalent to d by 2 into square root of k in air, where capital K is the dielectric constant for the given medium. And here it will be d by 2 into root k. Now, calling this equation number 2, we can use these two to find F prime in terms of F. Take the ratio. Equation 2 divided by equation 1 will give us f prime by f to be d square divided by d by 2 plus d by 2 into square root of k. What is k? 4. Square root of k is 2. And square this. 2 and 2 will get cancelled. Even d square will go away. What are we left with? 1 divided by 3 by 2 whole square. Simplify this further and you get 4 by 9 here. So what is f prime in terms of f? It is 4 by 9 times f. That's your final answer. Look at the options now. The correct one happens to be A.